Please go ahead.
Good morning, everybody. Today I will be presenting a paper that was recently accepted at NIPS conference, and it is titled Delay Gradient Averaging, Tolerable Communication Latency in Federated Learning. This paper is by the Sunghan group from MIT and also his students from Amazon and Google. So starting off, here's a brief outline of today's presentation. First, I'll speak about the motivation. Then I'll talk about this paper's main idea, which is the delayed gradient averaging. Then I'll talk about the theoretical analysis and then some experiments. And finally, I will conclude the paper. So we know that federated learning is a very important machine learning paradigm, which allows training without sharing the personal data. So if we have the user's data, which can be sensitive in nature, the users of the devices can use the data on the personal devices like mobile phone or Alexa, etc. And continuous training is performed on the devices, and only the model weights or the parameter updates are uploaded to the parameter server, which can be a cloud server or an edge server. And the model updates are broadcasted from the server back to the devices. So the two main advantages of having federated learning is one is the security, because the data never leaves the devices, and it promises this kind of security and regularization. And the other is customization, because models can continually adapt to new data coming from all the sensors, though they are only working on their own data, because the model updates is derived from several other devices' data. It can be more customized, and hence accuracy is much better. So the way federated learning works is you have several devices, and each device has their own data. The data owner has which is not shared with the aggregation server. Only the model update from each device is uploaded to the server, and the aggregation server broadcasts the updated model back to the devices. So this local training on clients is performed, and the global aggregation is performed on the server. The main goal is to minimize the objective function, where the objective function can be defined as in this manner, n being the number of devices or the number of data owners. And typically, local SGD is a method that is used inside of the devices to perform the local training. Introducing a small preliminary about the difference between the distributed training, not the distributed learning, but just the distributed training and the federated learning in typical scenarios is that most of the devices on the distributed training are all connected either through wired Ethernet or infinity band. So the bandwidth that is offered is much higher. It's almost about 100 Gbps. And the latency is very low because they're all connected with high bandwidth. And on the other hand, when it comes to federated learning, typical connections with the parameter server is through Wi-Fi or cellular network. And the bandwidth that can be offered is almost up to about 1 Gbps. So which means the latency is almost about 200 milliseconds. So if we have to compare the typical data center training versus the federated learning training, there is a huge gap between the network connection of these conventional training and the federated learning. So what happens because of this gap is there is a network bottleneck that kind of gets created in federated learning. So we know that several papers in the past, several papers that we have read and we've presented to, usually deal with this communication efficiency federated learning. So the main idea would be to improve the bandwidth by either gradient compression methods or like quantization, pruning, etc., or doing some hardware upgrade, which can enhance this bandwidth that is provided. So this is the most communication efficiency approach that is taken by typical papers. However, there is one challenge that is hard to achieve, that is the latency. So no matter how small you try to make the model update size and try to improve the communication efficiency, the problem would be the geographical locations of your different devices, especially in federated learning, when you have the devices and the edge servers sitting on different geographically located locations. For example, if you have to talk from Boston to Shanghai, even if you have to consider the speed of light, there is a physical limit. So it takes about, let's say, 162 milliseconds. So this is something that cannot be bridged because we cannot go about the physical limits. Also, there is signal congestion that happens. Even if you say you are using a Wi-Fi at home or you're using it in an urban office, it creates a lot of signal contention because you have multiple users. So these are the main challenges that we want to overcome in federated learning. So how more exactly to see how high latency slows down federated learning is, let's say that we consider this graph where you have the normalized throughput of your network versus the network latency that is offered. If you have the training that is happening within a rack, then the throughput delay might be about 1 microsecond. But if you consider that the same kind of training is happening within one data center, which is much larger, then the delay would be about 1 milliseconds to up to 10 milliseconds. If you keep going further, if you have Wi-Fi, the wireless, it goes up to 100 Mbps. And if you see very geographically distributed locations of your devices, then across the world, it can go up from 500 milliseconds to up to 1 second. So if this 1 second seems too small, but when you look at the normalized throughput of the network overall, it'll be about 5.8 times much slower compared to your distributed training within the rack. So we can see that the long distance connection slows down the training by a really big margin. So the existing work that we have seen mainly, which focus on the communication efficiency as such, also suffer from the high latency problem. Let's look at the very popular distributed synchronous SGD work. So there we usually sample and calculate the gradient, which are sent to other nodes. And after sharing the gradient updates from each other, the devices perform a local aggregation and compute a model update. So this is the typical flow of the algorithm. So what happens here is, let's say the blue boxes are computation, the local computation of the devices, and the yellow box is the communication. It happens sequentially. So let's say that computation took some time, then the communication is going to take this much of time, then communication. So it's an alternate cycle. Just in case that the communication increases because of all the physical limitations or the other bandwidth issues like we saw, then this yellow keeps increasing. So if you have to have a sequential way of doing first computation and then communication, so there's a lot of bandwidth that gets wasted waiting for these communication runs to finish. So the worker has to really wait for each transmission to finish before it can go on to the next step and continue the local training. And the other more important algorithm that we know of federated learning is the federated averaging, where in a similar fashion, the gradients are computed and shared and then aggregated. And we usually have a K value, which is the number of local rounds that is performed by the devices before the model update is sent out. And even over here, we see a similar way. We can increase the local computation, which most of the papers claim that you can, instead of doing one step of computation and one step of communication, it is better to do more rounds of local computation and then do the communication. So that way you would not be doing frequent communication and you won't be wasting the bandwidth a lot. So even when increasing the number of local rounds and increasing the K value, as the latency increases in communication, we would still face the same problem. So you have two steps of computation, then you're waiting for communication again. So especially when the latency is very high, then this becomes very slow. So we saw that the two most famous methods also suffer from the latency problem. So what is this paper proposing? So this paper is proposing a method called the delayed gradient averaging, which is the main method of the paper. So how do they improve the training through under this high latency problem? So they try to pipeline both computation and communication together. So it's a distributed optimization method, which can tolerate a lot of communication latency that federated learning usually offers. And it can scale even under high latency of even more than 1 second. So the key idea would be to delay the gradient averaging to future iteration. Instead of doing the averaging at every time, you will delay it. So I'll tell you more details about it in the following slides. So you somehow want to pipeline the communication and computation together. So you don't have to freeze the local computation power of your devices during the communication. So the other advantage of this method, it also accepts the stale average gradients for model updates, because it can use the gradient correction term to compensate for accepting the stale gradients. So more details about how this works. So the whole idea is, let's say that on the left, you have the typical scenario where there is no delay, and you have 1, 2, 3 local computation steps, local training steps. After that, you send the parameters, you receive the parameters, there's this small gap. After that, you continue to do your local training. So this is how all the local machines are blocked, and they wait for all the synchronization to finish. This gap is what this paper wants to cover by pushing the local computations in parallel with the communication that is happening. So the worker will keep performing the local updates while the parameters are in transmission to reach the others. So the main steps would be that in a similar way of federated learning, you would calculate the gradients. And here you introduce an extra parameter called D, which is a delay step. So if you're just starting your training, like iteration 1, then you send the fresh gradients to the other nodes. If for further iterations, if you have the delay steps introduced, then you will then you will continue the training, and eventually, like maybe at step 6, you will receive the scale gradients from all the other devices, using which you will perform the aggregation, and then you will continue with the training. I'll explain a little more details about how this tail gradient exactly works and how this update step works in the following slides. So further emphasizing on the main idea of this work is, let's look at the federated averaging. And let's imagine that this red line means the averaging step is taking place, whether on the server or on the devices in case of no servers. So you have, in case of one local round, you have one local round of computation, followed by one communication, and then the averaging takes place. Then the devices are updated with the latest model update, and then the next step of local computation, and this way continues. In case the latency increases, we don't see a lot of difference. Again, we are doing one step of each computation, communication, and then averaging. So in case we increase the local number of rounds to 2, again, we see the same. We see a similar behavior. After 2 steps and 1 communication, we see the averaging. So this is the typical behavior. So what happens if you use the delayed gradient averaging? So here we use the other parameter called D, other than K, which indicates how many delayed steps were happening before the averaging finishes. So let's say that you have K is equal to 1 and D equals 1 in this place. You have one local round of computation that happens, and at the red, you're sending the update to the devices. So which means the yellow block started, so the updates are going by. When they're going by, each device will continue to do the local computation on their own. And then finally, when they receive the update from all the models, they do the averaging, and then they send the updated gradient and again continue the local training. So we see that the computation, communication are happening in parallel. And in this scenario, even if the latency increases, and if we have a bigger bar over here and the yellow is increasing, it's still okay because we have somehow parallelized both the processes. And in case you
Pavana, hold on.
Yes.
For this, I have a quick question.
Yeah.
Did this paper talk about, can we do the communication and computing together? For example,
Yes.
in real world device?
Yes, exactly. They give real world scenario. They have a real experiment.
Okay. So even for our device, for any kind of mobile device, supposedly they can do this together, right?
Yes, they can do this together. So they show that that how they can be parallelized, and how the transmission can take place irrespective of whether computation is happening on the device or not.
Okay. Thanks.
Yeah. And in the similar fashion, if you increase the local number of steps, we see a similar way. And even if the latency increases in the communication, we are still okay because we continue to do the local training because our D value is set to 1 over here, so we can continue to do the training without waiting for the computations to finish.
So I have another question. Could you go back?
Yes.
For this solid line, right? The first solid line, that should be the time, the server aggregated the, gradient updates, right? But actually, as a solid line time point, what they aggregate is would finish in the dot line, right? My understanding is correct or not? Okay.
Correct.
Okay.
Yeah, so it's like whatever was sent out in the previous iteration is kind of aggregated, delayed, like in the next iteration. Yeah.
Okay. All right.
Okay.
Thank you.
So let's walk through these update steps in a step-by-step way. So let's say at iteration 1, the first let's say T is your communication rounds and K is your local computation. So at the first round, only the local updates are performed because you don't have any other updates with you. So at the end of the last local round, K+1, the update will be written in this way, like the usual update step that W equals W minus eta gradient. It's the same way. This gradient can also be written as the summation of the gradient computed at each local round. So K is your local round, and I is your per device, N is the total number of devices. So the 1 over here is nothing but T, the t value 1. So you have G, T, K, I. That's how the notation stands. So this is called as the accumulated gradient because the gradient is accumulated across each local round, across the mini batch, and finally, this is what you will be sending out to all the clients. So for simplicity, we can denote this as MTI. And at the end of this, the update is sent out to all the devices. So the other thing that this paper is talking is they are speaking in the absence of a central server. Like you do not have a parameter server which does the aggregation for you. They assume that the devices share the gradient updates with each other and they do the aggregation by themselves. So we see that the gradient updates, the accumulated gradient is sent to all the clients instead of sending it to the server. And instead of waiting for the transmission to finish, they will just immediately proceed with the second round of local updates. They leave the first round of averages in transmission. And by the time the update is received back to the device, the client will already perform D extra local updates in the second round. So this update step can be written as the W minus eta G. T2 is your T equals 2 here. And D is instead of K, beyond K, we also did the extra D number of steps. So we'll write this as B over here. And this can be simply written as the first initialized weight, W1, and eta remains the same. And the gradient update with the G2, it can be split as the gradient from the first round, the one that they sent out as accumulated gradient. So this is the accumulated gradient from the first round. And this is the gradient that was just computed in the D number of iterations by the local device. So we see that the update step contains of these two parameters, which is extra. One is the stale gradient and the other is the fresh gradient that was computed. So both of these are considered for the weight update. But fortunately, when you do this stale update, there is a issue that the staleness can create issues in accuracy and error. So this can be taken care later on through the gradient correction, about which I will speak in the next slide. So simplifying this further, writing it in a more simplified way, this can be written as M1 prime, M1 bar. And on simplification across the devices, because it is aggregated, it can simply be written in this way. This is called as the accumulated average, which is again sent across to the devices in the second round. And so at the end of the second round, the W2 update can be written as W1 minus eta times this accumulated average. So every subsequent round, you will have this as common on all clients because this is what we will receive back from the devices. All the devices will do the aggregation and send this back to us. So this will be common on all the clients, and minus the one that the device computed in these D steps when the transmission was happening. So when we did parallel computation, this is what we computed, and this is unchanged. This is unchanged. We'll reuse this. So this is what the delay gradient averaging looks like. So this is the main idea of this paper. Any questions so far? Okay. So next we'll talk about the guarantees of convergence that this paper offers. First, we assume that the function is Lipschitz smooth. So we see that the gradient difference will be defined by the L as the Lipschitz constant. And the second assumption that the paper has is that the gradients are bounded as well as the variances are bounded. And doing the computation of this using a convergence proof very similar to what we have, what we usually follow for the expectation of the final function output difference of the updated model, we can foresee that the convergence rate will come up to this kind of a parameter, where delta is your difference, sigma is your variance, and j is your number of devices or the number of machines, and n can be written as the number of iterations. So in this way, we can see the convergence rate of DGA is going to be this. So if we see that further, if we set this D value to be less than this particular value, then this algorithm converges very quickly. You can almost achieve the convergence rate as the original SGD problem, which is this value. So just this is the same as the original SGD, just that we have one extra term which includes the delay term, the D term, And like if we try to limit the value of D, then we can nearly achieve the same convergence rate as the original method. So which means that DGA not only helps us to do this pipelining, parallel computation, communication, but even the convergence is quite fast. And further, the main contribution of their paper, other than the delay gradient averaging, is the real experiment and the simulation. So first I will walk through the simulation, then I will walk through the real experiment. So for the simulation, they are using the CIFAR and ImageNet for the image classification task. And they also do the language modeling task. For that, they use the next word prediction on the Shakespeare. And they use the PyTorch, and they use the HorrorWord, which is distributed learning framework, which was proposed recently. So they use these open source of distributed learning framework along with PyTorch. And the model that they use for training all of these data sets is the MobileNet V2. They assume a 64 number of workers, and they also provide data augmentation by doing the random cropping and flipping, and also to avoid the gradient explosion, they do the clipping of the gradients, etc. So these are the settings. So using this, we see that the simulation results on all the three data.
Hold on, sorry.
Yeah.
I'm more interested in the hardware they're using. They're using a server or a mobile device or anything?
Yeah, they're actually using Raspberry Pi models. And they also use the Netgear router because they do not assume a parameter server. Like I was saying, it's just devices are sending the update to each other. So they just use the 8 Raspberry Pi models as the mobile devices.
Chenpei and Ray, I have a quick question for you guys. For the Jason TX2 or Xavier, can we do the same thing? We can allow the computing and the communication together? Can we allow that?
I think just like this paper, we need to, you mean we let the communication and computation doing parallel?
Yeah, work at the same time.
Okay.
Have you guys tried that before?
Yeah.
I mean, the paper's idea actually is very, very simple. Probably some of you guys think of that before, but you know, my only concern is, you know, can the device do the things together? Just like, you know, traditional, when we talk about the wireless communication, we cannot do the transmission and receiving at the same time if we only have one antenna, right? But if we have multiple antenna, somehow we can do that, you know. So I just want to get to know from hardware point of view, from CPU, GPU point of view, can we do it at the same time or not?
Actually, I think it can run in, for example, for the, I used to try the transmitting and receiving codes run in different sessions so they can do it at the same time. So I don't know, I haven't tried it. So if the learning and the communication, their codes can run in different sessions, maybe they can, it can be done at the same time, but I don't know.
Probably you guys need to try, right? For this one, it's different because it's a rack. My guessing is they use some of the Raspberry Pi, they do the computing, but they use some of them to do the communication. But you know, they're kind of you know, clustered together. So I don't know, probably there's a inside they can do some information exchange, something like that. What I'm asking is on a single device, say one TX2 or one Xavier, right? Can we, you know, execute the two commands simultaneously? Like one is do communication and the other one is do local computing together? Can we do that?
It can be, but it need to, I need to try that.
Okay, you guys just figure out, okay? All right, Pavana, sorry, please move on, yeah.
Yeah. So I will show the accuracy result first. So for the accuracy for both the IID or the non-IID partition, they use just the federated average as the baseline, but they are changing the number of local computations as 5, 10, and 20 respectively, and they see what is the amount of accuracy and what is the speed up. So they keep this one as the base, and they compare the speed up compared to this one, compared to this scenario, and they write the values of the speed up respectively here. And the highlighted column talks about this paper, the DGA, and they set the D as 20, so they can perform local computation up to 20 until the transmission reaches back. And they see that the speed up is way higher compared to what the federated averaging offers, despite changing the local computation values. So we see that we can also, the accuracy is higher than the federated averaging, and it almost replicates the base k equal to 5 value. So the accuracy is almost comparable to that. Maybe it's just smaller by 0.1 or 0.2, but the speed up offered is way better. So this is in line with the theoretical computations about the convergence that the paper claims. So the performance of the system is not altered by doing this kind of parallel communication and computation. And this was the hardware real world experiment benchmark that they try to set. So they built a cluster, the Raspberry Pi cluster, to emulate the real world settings. And they have 8 number of Raspberry Pi 4B models, and they consider 2 racks of the same settings. On the left and the right, do you see the same settings? You have 8 devices each, so in total you have 16. And the device OS specifications are in this fashion. They're using a Debian, and they use a router in order to simulate this the wireless. To provide the wireless connection, they use a Netgear router with the OpenWRT OS, and the experiment are conducted in both the racks, and they also test for the delay in this speed up. So okay, it's the next slide. Okay, no. So the speed up comparison between the federated averaging and the DGA for this Raspberry Pi cluster is in this way. So they keep increasing the number of nodes that take part for participation. So for one node, up to 8 nodes, because they have the 2 racks. So they do going rack-wise. So they do computation on the 8 and the communication on the 8. And they check what is the speed up that is offered in each case. So the blue bar is the federated averaging. The green is the federated averaging with 10 number of local runs. The yellow is the DGA method with 5 local computations and a delayed iterations of up to 20. And we see that this proposed method demonstrates some ideal scalability even in a very high latency environment. We see that up to 7.1 and 7.8 can be the speed up offered in case of an LSTM in language model, or the CIFAR and ImageNet in case of mobile net. So this is almost close. The accuracy, though, is almost close to what the typical algorithms offer. The latency that the speed up that it achieves despite the latency is almost comparable to what the data center achieves. That whatever conventional algorithms you use inside the data center, we can almost achieve that amount of speed up. And the next result is from both the simulation and from the real experiment. This is purely in terms of latency. And for the simulation, to simulate the latency, they use the NetM. NetM is a network emulator, which is an open source code for simulating the different latency values that you want. So they try to do a synthetic latency from about 1 millisecond to almost 5,000 milliseconds. And again, they use federated averaging as the baseline with different local computations, 5, 10, and 20 respectively, the blue, green, and red. The solid red is the one offered by this method. And we see that the throughput is way higher compared to the federated averaging. In federated averaging, we see this small improvement in the throughput as the number of local computations increase, but still it's not as good as what we expect or what this method is offering. And coming to the real experiment, to simulate this kind of latency, what this paper is doing is they use 4 representative cases. where you have one is the wired, the other is your wireless. And in the wireless, you are they have three scenarios where you have the devices kept in different rooms, and you keep them. Second is keep them on different floors, and the next is keeping them in different buildings. So this way, you kind of we can emulate this latency values of 1 millisecond, 16, 132, and 470 milliseconds respectively. So they took those values over here to plot this graph. And after placing these cluster at different locations, they try to emulate this different quality of connection. So we see that different from the simulation, where the simulation you are only trying to do a synthetic latency. In the real experiment, we can see that there can be some issues in the wireless connection because of the real experiment. There can be some network straggler, some unexpected packet loss, or some other unpredictable, real scenarios can come into this experimental setting. So those can be challenges. So, but what this paper claims is, despite those unexpected packet loss and other challenges, they're still able to achieve some good throughput degradation despite so much of latency. Even after up to going up to 470 milliseconds of latency, they're still almost achieving a very good throughput. And in comparison with federated averaging, doing the same this experiment on the same settings, they were seeing that federated averaging performs much worse than this method. So in both the latency settings, whether it is synthetic or a real device experiment, we see that the federated average performance will start to degrade once the latency increases, because initially they all start off at the same throughput. But DGA's performance, even under high latency, is still remarkable. So these are the main things that this paper offers. Next, I have the conclusion, where we see that this paper designed the delayed gradient averaging method, which delays the averaging to a later iteration so that high network latency can be tolerated. And they also proposed a new update formula, which can not only provide the update in terms of this parallel computations, but also it can compensate for the staleness of accuracy that can be offered by accepting the stale gradients from the other devices. And we also saw that they did some real world experiments, and they also showed the convergence and accuracy, both in terms of theoretical and empirical results. And the training throughput was also observed under the real world Raspberry Pi cluster. So any questions?
Questions, guys? I'll stop recording if there's no questions.